Okay, video 5 of the Schneider Modicon expansion modules, we're taking a look at sourcing DC using a relay style of TM3. Specifically, the model that we are going to be illustrating in this video is going to be the TM3DQ, that's discrete, Q being output, 8R, meaning that it's got 8 relay connected outputs that we are going to have off of it. You can also take what you learned in this video, you can expand it out to the DQ16R, which is the same module, just with many more outputs that we are going to go and have. We're dealing with sourcing inside of here, and syncing and sourcing can sometimes be misunderstood. Sourcing literally means direct connection of the positive of my supply to the reference or to the common terminal of whatever my input is going to go and be. And when I'm doing this on a output, it would be an application of IEC positive logic. If you are unfamiliar with what syncing and sourcing and IEC positive logic and negative logic are, go through to video number 2 out of the M221 series. There is a complete video that explains it all in depth. Hopefully then you come back with an understanding of what they all are. Do note as well that sourcing and positive logic do not always go hand in hand. Positive and negative logic both use syncing and sourcing, but they use it on separate sides of the PLC, input or output. Okay, let's move into our data sheet before we actually start on to the component. What we're dealing with is a model that can work with any one of these main PLCs, the 221, 241, 251, or 262. They're normally open connections that we are going to have, relay connections that are able to go and handle 24 volts DC or 240 volts AC. And the reason that we have a much lower value of DC is simply because a DC current is much harder to go and interrupt. It's a solid current, whereas AC does travel through that zero axis enough that it's easier to go and interrupt. The other thing that we see down here is the current rating is written in a little bit of an odd format. Usually you would go and write this just as being 2 amps, but for whatever reason, Schneider has decided that they want to go and write this as 2000 milliamps. It's the exact same value. They're just using a different, engineering range that we have off of here. 2 amps is not a huge output. You're not going to be driving loads themselves directly off of it, but you're going to be using this to switch out other control components, contactors, and the like. If we go a little bit further into the data sheet, we also find out that there is going to be additional information, such as the response time is going to be 10 milliseconds to go and turn on, 5 milliseconds to turn off, that the actual relay itself is rated for up to 20 million cycles that we are going to go and have off of it. They give us a couple of guidelines for our cables that we're going to go and use, no more than 30 meters that we're going to have. And they tell us a little bit about the insulation levels that are going to go and exist between each of my individual components. Now, as we said in the previous data sheet that we were just looking at, or previous section, it is only rated for a maximum of 240 volts. These are not voltage ratings. These are just going to tell you about if you end up with a fault on the system and you get a transient that's coming through, it's going to be able to go and insulate up to these voltage levels. But do not try to operate at these voltage levels. You will for sure destroy that component. The next thing that we look at is going to be our data sheet. Now, our data sheet over here does have 2 separate drawings that we are going to go and have. We need to analyze which one we need to go and use because we're not using all these drawings all at the same time. They're just trying to illustrate everything at once. First of all, we're going to go and scratch out a couple components that we know we're not going to use by defining which side is going to be sourcing. If I take a look, sourcing is going to be applying a positive to the common, which then switches through out to my components. Syncing would be applying a negative to my common, which would then switch out to my load. So we see that this drawing that we have on this side is going to go and be the syncing configuration. We are not doing this video about syncing. That's the next video if you want to learn about syncing outputs. We are dealing with sourcing, so we're going to deal with this one. The other thing that we're going to look at is we are not using a AC input over here. They do show AC right next to the DC. They're showing us that we could do either an AC sourcing or we could do a DC sourcing, not both simultaneously. So we're just going to scratch that out and look at what we are specifically dealing with here. You'll see that we've got our DC source. We're supposed to go and take the positive of that DC source. We run it through this. This is going to be a 7 amp fuse that we are going to have because that 7 amp fuse is going to feed into the common, and from there it feeds out to every single one of these over here. What we see is that on the output, they also suggest that you go and have a fuse coming out of here. You're taking that positive out. They're suggesting a 2 amp fuse for those. They do suggest type T, which are harder type of fuse and fuse holder to go and find. And then we see that we take that positive through to my load itself, and then from my power supply, we then wire a negative back to all the rest of my loads, the way that they're shown over here. There is also a note on the data sheet, and this note does show that our load has got a little device connected across that. That's just to go and help maintain the integrity of our relay contacts. It's going to be used to suppress any little bit of inductive kick that we would get off of them. Okay, so we're going to be working from this drawing, translating it now down onto the physical. Before we do that, let's take a quick look at what we'll use for fusing and fuse holders. We're working off of a DIN rail installation, so we suggest a DIN rail style of fuse holder. You can either get the larger ones that take a class CC fuse, use the HCLR type, which are going to be fast like that. Use a lighted one as well, so you can tell visibly when you lose a fuse off of there, or you can go and use the skinnier type that take those smaller glass or ceramic style of fuses. Once again, do make sure that you are using something that has got indication across. It just makes your troubleshooting, your customer's troubleshooting, that much easier to deal with. The other component that we saw on the data sheet was going to be the suppressor module. That was that small component right over here that we were looking at that has to go across our coils. This is what a suppressor module itself looks like, and from 24 to 250 volts DC is what this thing can go and suppress. It's actually rated for AC or DC. And it is just going to go and have diodes. If you take a look, it's the symbol for a back-to-back Zener set of diodes. What you do with these is you are going to go and take them to your contactor. You got your 24 volt contactor. You are going to go and bring in that point over there, and it connects in directly across the coil. You snap it in. It doesn't make any of your wiring any more visible. It's actually completely hidden on the back side or along the side of your contactor when you are using it. That's the one that we see over there. Okay. Now we are into the actual wiring that we have. So we are using for this specific one a M251. That is going to be our main PLC brain. We're going to follow in our AC. That's our AC input. We're taking our AC in through a DIN rail breaker. From that DIN rail breaker, we're running that thing into a DC power supply to convert it to 24 volts DC. And then from that 24 volts DC, we see that we are running power into a fuse holder that runs into run my main power for my M251 PLC. But we also see that we are running 24 volts. We're just dropping off over there, and we're bringing it over to this fuse holder that we are going to go and use on this section over here. So that's our supply of power that we have into here. Let's start with our wiring. Now, we said that we were going to be using sourcing, which means that we have to come from our fuse holder to our common. So we're going to go and do that. We're going to come from here, and we're going to go and run to our common. We're going to bring that one into the top, and actually let's bring one into the bottom section as well, because if I wanted to wire anything out of here, I would need to go and run components off of that one as well. So if you're going to run through both sections, this common feeds this whole group over here. This common up top feeds that whole group over there. So we're going to bring it into both of these if we're going to run both off there. I do also want to just zoom in a little bit here on this terminal strip that we have over here. We do see that there is an NC right over there. That NC does not mean normally closed. It means no connection. It's an unconnected input that we are going to go and have. Some cartridges actually don't have the screw in there. I've left all the screws into my drawings here, but some of them don't have a screw. Some of them will have a screw, just don't connect anything onto it. We'll zoom back out over here to full size. All right, so we have brought our power in. What we then need to do is we need to go and run from our power over to whatever it's going to be. We're going to take relay 0 over here. We're going to use that to run this first contactor. So I'm going to run that in to my A1 or my coil of that contactor. And then from the other side of that contactor, we would then run from here back to my DC supply. So we're going to go run through, and we're back to my DC supply. You should always be able to complete a path all the way through your components. Over here, we see that we are going to go and have DC brought in. We bring DC up into the card. We can run it through the card and then back down through the coil of my load over here. It's a 24 volt DC coil back to my supply like that. We have a complete path for current flow, so we know it's a good connection. We'll take a look at the other one that we have over here. We're going to say that we're going to feed that one out of the lower group down here. Same format that we're going to follow through, except this one has got the addition of an overload block on the bottom over here, which is designed to go and measure the current that is running through my contactor over here out to my loads, and it's going to go and trip out. What we want to do is we want to make sure that whatever we're sending out for here is going to be able to go and respond to that. So we will take our power out. So we'll take this one here. Let's pick it from number 6 over here. We're going to take that number 6 out. we are going to go and feed it in through a normally closed contact over there, then out of that normally closed contact up to my A1 like that. And now that we're at my A1, then all we need to do is take my A2 all the way back. We'll tie it in underneath this screw over here, no more than 2 wires under a screw. And now we have got a path all the way back from my DC. Let's just trace through that one as well really quickly. We see what DC being brought in through my fuse holder. DC then travels down to the common of my card, travels through my card, travels up through the normally closed contact of my overload, hits the coil itself. From the coil itself, it is then able to go and travel back along my negative to my DC supply. We've got a complete path for current flow. This is a operational set of relays. Okay, that's the end of this one here for my sourcing. Sourcing is, by the way, your safer one. We're going to take a look at syncing outputs on the next video. There is a little bit of danger inside of those.